So, you've realized your school is doing medical physics, and you're reviewing the content right now. It's long. It's very long, and you're wondering how you're gonna remember everything. Well, worry not. I'm gonna teach you. Well, not everything, not the whole course, but I can teach you ultrasound. Well then, what is ultrasound? Ultrasound are sound waves with frequencies above 20,000 Hz. As humans, we can only hear from 20 to 20,000 Hz, meaning we cannot hear ultrasound. There are certain animals such as dolphins and bats which are able to hear ultrasound, as well as use ultrasound for echolocation, as well as that we have man-made structures such as submarines which use sonar detection, similar to how echolocation works, using ultrasound. Sound waves are longitudinal, meaning it needs a medium to travel in. This can be air, liquids, and solids. The speed of sound in air traveled at 330 meters per second. To produce sound, we need a vibrating source to push air back and forth. To produce ultrasound, we need to push air back and forth at a high frequency. In medical physics, we need the ultrasound waves that transmit from the air to the skin. The way ultrasound waves work is that they get partially reflected and partially refracted when meeting a boundary of two different mediums. On the screen, I have shown you a diagram of the two different mediums, air and skin, and also showing the incident sound approaching the boundary as well as the reflected sound and the refracted sound. In situations like this where we have two different mediums and sound approaching the boundary, we want to know the fraction of the ultrasound intensity reflected at the boundary. This all depends on something called the acoustic impedance of the material. On the diagram on the right, you will notice the two Z's, Z1 and Z2. This represents the acoustic impedance. Acoustic impedance is the density times the speed of sound in the material. In scenarios such as this, it is important to have the impedance of both the mediums to be relatively the same. This is because so that there is no reflection when the ultrasound is passing through one medium to the other. If the impedance of the two mediums are largely different from each other, then it is likely that most of the ultrasound will be reflected off. To check whether most of the ultrasound will be transmitted, we can use the equation for reflected intensity, which is the incident sound divided by the reflected sound. The impedance of the skin and the air are likely going to be different. Both the density and the speed of sound in the mediums are different. So, how do we counteract this problem? We use something called a coupling medium. A coupling medium is a gel that we place onto the skin. Now, the impedance of the coupling medium and the skin are relatively similar, so when a transducer is placed onto the gel and the skin, the ultrasound is able to transmit through the skin with barely any reflection. We also have another factor into play which is called attenuation. So this is a general term that refers to any reduction in the intensity of the signal. It's a natural consequence of signal transmission over long distances. In hospitals regularly, we use sound waves that are 1 to 15 MHz because it's the best frequency due to its fine balance between spatial resolution and image depth. Higher frequency waves produce narrow beams because they refract less, which gives them a higher resolution, but they are more attenuated, so lower frequency waves must be used for images deeper in the body.
To generate a signal from the ultrasound transducer, a potential difference is applied across a piezoelectric crystal, which causes it to expand or contract depending on the direction of the current. By applying an alternating voltage across the crystal at the resonant frequency of the crystal, it vibrates at the same frequency as the alternating current. These vibrations produce ultrasound waves, which are transmitted into the substance the transducer is in contact with. The transducer can also act as a receiver and detect reflected ultrasound waves, using the piezoelectric effect in reverse. A special property of the piezoelectric crystal is that when a pressure is applied to them, they produce a voltage. The varying stress from the ultrasound induces a varying voltage across the crystal, which can be used to interpret the frequency of the reflected ultrasound waves. The use of ultrasound has several advantages and disadvantages. The advantages are as follows. The use of it produces no side effects and no known hazards. It is non-ionizing radiation, and it produces real-time images. It produces good images of soft tissue and is relatively cheap and portable, when compared to other medical equipment. The disadvantages are also as follows. It doesn't penetrate bone, so it cannot be used for fractures or to examine the brain. It cannot pass through air spaces in the body, for example, through the lungs, which is due to the difference in impedance. Depth of penetration can be limited. Resolution is poor, which makes it hard to see the fine details of an image. It cannot give information about solid masses found, and highly skilled operator is required to produce a good image.
これは運がいいわけでも腕がいいわけでもないんだ。
じゃあ何が？
切符がいいのさ。